Okay, assalamualaikum and good day. Today we are gonna take a look at gain compensator design for control system. This design is via frequency response. So let's take an example here where our transfer function is 0.5 over s squared plus s, and our desired overshoot is 19%. So I will go through the step to design it, but first let's simulate the original design without gain and see the output response. So if we need to, okay, we can see that the steady state is not within the period of the simulation. So for my simulation, I simulate for 10 seconds, but it still not reach the final value. So we can increase the simulation period, let's say to 30 seconds, and run it back. And then okay, you can see the whole output response. We can verify our overshoot. Just click the bi-level measurement. Okay, the overshoot of the system right now is 4.737%. So our task is to design the system to gain an overshoot of 19%. So the first step is to find the first gain to make the magnitude of the system in body plot equals to 0 dB at frequency 0.1 radian per second. So how can we find the K? So first we just right click at the block and choose the linear analysis, and then the linearized block. We can see the body plot, and then we click the icon. Okay, so the first step is to find the first K that can make the magnitude 0 dB at frequency of 0.1 radian per second. So right now, what is the magnitude at 0.1 radian per second? We need to check first. So 10 to the power of 0 is 1. 10 to the power of negative 1 is 0.1. So we can measure it. Okay, by zooming at the appropriate position. So right here, around here. Okay. So from here we can click at the response. So we get 0.1 equals to 13.9 dB. So our task is to reduce the magnitude to 0 dB at frequency 0.1 radian per second. So in order to reduce the magnitude, we need to deduct or minus our system with a gain that equals to 13.9 dB. So right here we know that at 0.1, so this is before, at 0.1 radian per second we get 13 point, okay, 13.9 dB. So here we got 13.9 dB. So we want to reduce it to 0 dB. So we want it to become 0 dB at 0.1 radian per second. So what we can do is we need to subtract our system with 13.9 dB. So we just need to find what is the value in K for negative 13.9 dB because we are subtracting it. So the formula is 20 log K equals to 13.9 dB. Negative, we want negative. So K will be 10 to the power of negative 13.9 dB over 20, which is equals to uh, around 0.2010, around that number. So we now know that the K is 0.2010. Okay, then we can erase all of this. So now we know the first K will be 0.2010, around that number. Okay, and then we want to push our overshoot to 19%. So to calculate our desired phase margin, we can use this formula lah. So this formula, and then this formula, and then we get our desired phase margin. So I have calculated the value. We will get around negative for 49.12 degrees. 49.12 degrees. You can calculate your own at your own time. Okay, so we have the phase margin equals to 49.12 degrees. But first, let us verify that now the magnitude at 0.1 radian per second is 0 dB. Okay, so we need to place the first gain. So we can search for gain. And place it here. Okay, and then the value of our gain is equals to 0.2010. 0.2010. So okay, let's take a look at its body plot. Okay, since we have two blocks, now we cannot use linear analysis and linearized block by right clicking on each block. We need to uh, group the block. So I can choose both block, and then I right click and create a subsystem from selection. So now those blocks are inside this subsystem. It is in here. If you double click, you can see that it is in the subsystem. So I can right click on the subsystem, and then I just choose linear analysis and linearize those blocks. So in this page, we need to press board plot 1, so it will generate the new board plot. So you can see now that the second simulation produced at frequency 0.1 radian per second is equals to 0. This is 0.1, 0, right? 0.1, approximately 0.1. So we got 0.00. So it is actually 0. So the next step is to find the frequency omega radian where phase angle difference from negative 180 degrees is equals to phase margin. So we know that our phase margin is equals to 49.12. So we need to find where the phase margin happen between negative 180 degrees and another value. So we just let's assume that another value is x. We just say that negative 180 degrees plus phase margin is equals to negative 180 degrees plus 49.12 degrees. So we get negative 180.88 degrees. So we just search for negative 130.88. Okay, I can right click on the graph and click full view, so we will return to the original view. I can delete this cursor, and I can delete the older body plot. Okay, now we need to search for negative 130.88. Okay, to make our task or job easier, we can use the properties to adjust our limit so that we can actually precisely zoom at our desired location. For this case is negative 150.88. So adjust the phase from negative 131 to negative 130. Let's say 30. So we still don't see the second decimal point. We can further zoom the response. We'll take a look at 130.8 until 130.31. So we know that 130.88 is around 130.9. So let's just say it's around here. Let's turn on the grid to visualize it. So around, I would say it's around here. So we got 0.866 radian per second. So we can write it here. Our frequency is 0.866 radian per second. Then we want to find the second key by adjusting the magnitude at this frequency to become 0 dB. So we need to take a look at what is the original dB at this frequency. So we can change the limit for the time to the rate frequency to 0.86 until 0.9. Okay, okay. For 0. How about 0.8 until 0.9? No, 0.866 until 0.9. 0.866. I think it's around here. 0.866. So we got negative 21.1. Okay, let's check the answer. 0.866 is equals to negative 21.1. Okay, so we know that before is uh, negative 21.1 dB at 0.866 radian per second. So after we want it to become 0 at this frequency, 0.866 radian per second, we want it to become 0 dB. So we need to plus, because this is in negative value, we need to add. So the formula is 20 log k equals to negative 21.2. So the k will be 10 to the power of negative 21.2 over 20, which is equals to 2.28, sorry, 11.3501. So the second k is actually equals to 11.3501. So we can add the second gain. So we can add the second gain. We can add in the subsystem or at the outside decimator. So we can add another gain equals to 11.3501. Okay. So we can return back and check our border plot and click border plot 1. So the next one is the blue one. So okay, we can see that at 0.866 now it becomes 0. So supposedly our output response now has 19% overshoot. So we can click simulate and then check for our response. So okay, we can see that now the overshoot is 18.45%. So basically you can also multiply both gain because this is a linear. So 0.2 times 11 is equals to 2.2814. Okay, so similarly if I press run, we will get the same response. So we still got 18.45%. Okay, that's all from me. Thank you. Sayonara. Arigato.